Hi everyone! Today we're going to be talking about optical mineralogy, and this is part 2 to the first video I did on optical mineralogy. If you want to go check that out, I'll link it up here. In that video, we talked a lot about the optical features that we can use to identify minerals, such as those shown on this mineral identification chart. I showed this at the end of that video. Basically, this chart shows refractive indices, their associated mineral, the prominent cleavage planes and cleavage angles of these minerals, the interference colors of these minerals, and the birefringence values of these minerals. Now, refractive indices, birefringence, and interference colors are all things we talked about in the previous optical mineralogy video, the part 1 to this video, and then cleavage planes and cleavage angles are things we talked about in the first focus mineralogy video I did. I'll link it up here if you want to check it out. Basically, it was called something like mineral colors, crystal habit, cleavage planes, all of that. And then I also talk about cleavage angles and Miller indices a little bit more in the Miller indices video. I'll also link it up here if you want to check it out. But in today's video, the diagnostic features that we'll be talking about in terms of how to identify minerals using optical mineralogy include symmetry, which in this chart is a column used to identify whether the mineral is uniaxial, biaxial, or isotropic. We talked about the difference between isotropic and anisotropic minerals in the last optical mineralogy video as well. Basically, isotropic minerals are just boring under thin section because they remain in extinction for reasons you can find in that video, but I'm not going to repeat myself. So anyway, symmetry, basically what we're going to be talking about today regarding symmetry is uniaxial versus biaxial minerals and how to identify or distinguish between these types of minerals in thin section. Then we also are going to be talking about the optic sign and optic angle of minerals in thin section as well. The optic sign can either be positive or negative, which is why it's labeled this positive over negative sign in the chart, and the optic angle is labeled as 2V for reasons we'll talk about later as well. So theoretically, if you've watched my other mineralogy videos and you're going to watch this one, you will know how to read every single property of this chart and identify basically any mineral using optical mineralogy by the end of this video. So let's get started. First, I just want to recap that there are 7, well, depending on what textbook you're using, 6 or 7 crystal systems that crystals can be associated with, just depending on their structure, basically. And so these systems include isometric, tetragonal, orthorhombic, monoclinic, triclinic, hexagonal, and trigonal. We've already talked a lot about these crystal systems in previous videos. I even have a song. If you want to know how to remember them better, I'll link it up here. But in this video, the only reason this matters is because the crystal system can affect how the mineral affects light that's passing through it in thin section. And so, for example, when you have tetragonal and hexagonal minerals under thin section, they will affect light in the way that they have a minimum and a maximum RI, whereas orthorhombic, monoclinic, and triclinic have a minimum, intermediate, and maximum RI. So 2 RI values versus 3 RI values. So now you're probably wondering, what the heck is an RI value? Well, that is the refractive index. If you're not sure what refractive index means, I talk way more about it in the part 1 optical mineralogy video if you want to check it out. But for the purposes of this video, you can just think of it as how much the mineral causes the light passing through it to slow down. And so some minerals have only 1 RI value, such as isometric minerals, which is why that crystal system is not listed here in terms of minimums and maximum RI values, because they don't have a min and max. They just have 1 RI value, which is why they're boring under thin section and only appear black or in extinction. However, some minerals have a minimum and a maximum RI value, giving them beautiful colors because of what's called birefringence, which is also something we talk about in the first part of the optical mineralogy videos. This whole video is going to be me saying, go watch that first part. So if you haven't watched that, really go watch it because you're not really going to understand this video without it. So I'm really sorry. There's just a lot of terminology you need to have from that first part to understand what I'm talking about in this video. So welcome back. Now that you've gone and watched that, now you understand what RI is and that some minerals have multiple RI values and some don't. Those that don't are isometric, and we're not going to be talking about those today. However, those that do can have 2 RI values, a minimum and a maximum, such as tetragonal and hexagonal minerals, and some have 3 values, a minimum, intermediate, and maximum RI. And these RI values basically just vary depending on the direction that the mineral grain is oriented and the direction that light is passing through that grain. And so we can represent these variations in RI by direction by what's called an ellipsoid, known as the optical indicatrix. This is the main thing that this video will be about, is this indicatrix thing and how light passes through it and how we can orient the grain under the thin section to understand how the light passing through it looks at a certain way and therefore identify the mineral. So So what's this meaning of epsiloid? So you've got this oval shaped thing here that represents the optical indicatrix of the mineral under thin section, or the crystal grain that you're looking at under thin section. And you've got something called uniaxial and biaxial. We'll go over biaxial in a little bit, but first let's start with uniaxial because they're a little bit more simple to define. So the indicatrix for tetragonal and hexagonal minerals, which as we recall have only a min and max Ri values, so that's why we'll talk about them first. It's a little simpler than talking about 3 different Ri values. So the indicatrix for these minerals is an epsiloid with an axis of revolution along the C axis, or the up and down like Z axis. And so if we go back for a second, we can see that they mean this up and down crystallographic C axis. And like we talked about in the part 1 video, light can vibrate in different directions. And if the light is vibrating parallel to this axis of rotation, it is called the extraordinary ray, and it's labeled E. And the light vibrating perpendicular to this axis is the ordinary ray, labeled O. So we have the E ray or E direction and the O direction for the O ray labeled on both of these epsiloids. And if the E ray or extraordinary ray represents the maximum Ri value, the maximum refractive index, the indicatrix is called prolate. Whereas if the E represents the minimum Ri value, it is kind of short and fat. It is oblate. And a prolate indicatrix is positive in its optic sign, which is why you have this positive label here. Whereas if the indicatrix is oblate, it's labeled as negative in its optic sign. Now, if none of this is making sense to you, don't worry. At this point in the video, I agree, it's really kind of fuzzy and I'm just throwing a bunch of terms at you, but I promise I'm going to bring it all around at the end and you're going to understand it, because we're going to go over all these terms one more time after I kind of introduce them all to you, if that makes sense. Just trust me, stick around. I promise it'll make more sense. So bringing this into a perspective now of actually applying this to looking through a microscope at a thin section, if your mineral grain is oriented so that its C axis, C crystallographic axis, or axis of revolution is parallel to the axis of the microscope, the axis of like looking down into the microscope, then the thin section would be a cut of a circular section through the indicatrix. So these cuts are shown in the examples in this figure. So as we can see, these epsiloids have these gray circles, these gray cuts through their center, and that would be the cut of the thin section, or that would be represented by the cut of the thin section if your C axis, or basically this red line here, is parallel to the axis of the microscope. Now, this circle section indicates that if the mineral grain was cut like this, that light vibrating in any direction would have the same refractive index, because you can imagine it's circles, so light vibrating any way is going to have the same magnitude of refractive index. And because we know that if the mineral has the same refractive index, no matter which way you rotate it, it stays in what's called extinction. It stays black under the microscope. And so you'll just notice that no matter which way you rotate it, you can't get it to come out of extinction. And that is when you are looking at this specific orientation of the grain in this special direction, which I put little asterisks around because I just love the way my textbook worded that. They said this special direction in which light passes through the indicatrix is called the optic axis. So if you have light passing through parallel to the optic axis, which is labeled OA in these figures, then it's going to remain in extinction. You're not going to see any change in color or anything as you rotate the stage of the microscope. However, that can be misleading because you might think that, oh, that means it's isotropic. Not necessarily. That can be an anisotropic mineral that is oriented in the thin section along this special direction. So a mineral with an indicatrix that has only one optic axis, or this special axis here that is labeled here in red, then it is called a uniaxial mineral. So now we're finally defining uniaxial for you. I told you it's going to come back around. I promise we're going to get to it. So uniaxial means one optic axis. Biaxial, as you can probably imagine, means two optic axes. Yep, you guessed it. Good job. So now we can see here these figures shown here that we were talking about with, for example, tetragonal and hexagonal minerals have one optic axis and they are uniaxial. Whereas if you have these two optic axes, these are biaxial minerals. So what crystal systems do these minerals belong to? Well, you remember at the beginning of this lecture, we talked about how orthorhombic, monoclinic, and triclinic monoclinic minerals have a minimum, maximum, and an intermediate or in between RI value, well, that makes them biaxial. And you might think, well, that's 3 things. Why is it biaxial, not triaxial? Well, remember that biaxial is defining that there are 2 optic axes. It's not defining how many RI values there are. There are 3 RI values, which makes the epsiloid a triaxial epsiloid, and the indicatrix basically has an X, a Y, and a Z axis shown here in this figure to the bottom right. We can see the Z is basically like our C crystallographic axis we were talking about earlier. The X is going off into the right, and the Y is coming out at us. Now, that's not to say that the uniaxial epsiloid is 2-dimensional. It is 3D, but the X direction and the Y direction that would be represented by the uniaxial figures are the same magnitude, and so therefore they basically just have an X and a C, or whatever you want to label them, C, Z, whatever. But basically in the biaxial mineral, the Z is the maximum RI axis, the X is the minimum RI, and the Y is the intermediate. And so we have an axis that represents each one of these RI values, 3 RI values rather than just 2. So in this triaxial epsiloid, we have 2 circular sections that cut through this intermediate or Y axis. And if the thin section is cut through either of these circular sections, the grain would remain in extinction. Why? Because if we remember from our uniaxial example, if it's a circular section through the indicatrix, then light vibrating in any direction would have the same RI value, and therefore, no matter how you rotate it, it would remain in extinction or remain black under the microscope. And because there are 2 circular sections you can find in these triaxial epsiloids, this means there are 2 optic axes that go through these circular sections, and that means that the mineral is biaxial. And the angle between these 2 optic axes is the optic angle, or the 2V angle. And in terms of optic sign, if the Z or maximum RI axis lies in the acute angle, the mineral is biaxial positive. And if X, or the minimum RI value, lies in the acute angle between these 2 optic axes, then the mineral is biaxial negative. And in this case, we can see the mineral seems to be biaxial negative. But as you can probably imagine, when we're looking down at a thin section, we're not necessarily looking at a perfect diagram of the mineral's optical indicatrix. So how can we bring this into the real world of what we're actually going to see in the thin section and determine all of these things, the optical indicatrix, whether it's uniaxial, biaxial, the angle, the sign, all of these things are a little bit more complex to figure out when actually looking at a mineral grain under thin section. So let's talk a little bit about those complexities and how we can get around those to figure out these values of minerals so that we can identify minerals. So remember how we define the indicatrix as a representation of how the RI varies with direction in a crystal. Well, previously on the part 1 lecture, we discussed the difficulty of measuring the true extinction angles of minerals because the mineral grain is not always in the ideal orientation to measure these values. And so having a tool that could tilt mineral grain orientation under thin section rather than just rotating the stage would be really helpful. These tools exist, and 2 tools that are really helpful to do this are called the upper swinging condensing lens and the Bertrand lens. So let's quickly talk about how these lenses work and how they quote unquote tilt minerals under thin section. So if we flip what's called the upper swinging condensing lens, shown here and labeled as just condensing lens in this figure, we will see that light is now going through the mineral at different angles rather than just straight through the mineral. This is helpful because light is traveling through the indicatrix of the crystal at many different directions. So even if you have a circular cut, a circular section through the indicatrix, light has changed direction to the point where you will have variation in RI values, even though it's a circular section, and therefore it's not going to just remain in extinction. You're going to actually see the variation in RI values through what's called interference colors, like we talked about in the last video, and those interference colors can help you identify the mineral a lot more than just a grain in extinction. So that's really helpful. But there's a problem when the light meets the objective lens. The oblique light, the light that passed through that mineral at an angle, is lost, and you're basically just getting the light that passed through parallel to the microscopic axis. And that's basically the same as if we had never changed the condensing lens at all. And that's that doesn't help at all. So how do we actually get to see this oblique light? How do we refocus it back to our objective lens and to our eyes so we can see what's going on with the oblique light that's passing through that mineral? This is where the Bertrand lens comes in. This fixes that problem. Basically, the Bertrand lens refocuses the oblique light back into the focal plane of the ocular lens, and we can then see what's going on when that oblique light passes through the thin section, rather than just the boring old parallel light that passes through that thin section. So I guess I'm a little ahead of myself because I already said the sentence. Basically, I'm just restating that because this oblique light passes through at an angle of the thin section rather than just straight through it, the circular section of the indicatrix is no longer fully in extinction. Instead, the oblique light produces interference colors. Man, I'm really just ahead of the game today. But I guess something I didn't mention earlier is isogyres. So when you get these interference colors, you only get them where the oblique light is being refocused back into the field of view. Where the straight light is coming through, that parallel to the microscopic axis light is coming through, that's still going to be in extinction. And so this is going to cause you to have like black lines in your field of view that are called isogyres. These isogyres kind of look like this, typically like a cross if it's centered in the field of view. And this is called an interference figure. So what you'll have is this black cross because that represents the light that's still in extinction. And then you'll have these 4 quadrants on the outside of this black cross that are interference colors. So they're not black, they're actually showing the colors produced by the oblique light passing through your thin section. And if the grain is tilted so that your interference figure cross is not centered in the field of view as shown here, you can rotate the stage until it sweeps across basically to find that center of your cross. This kind of looks like this example here. If it's centered, this is a quartz example which has low birefringence, therefore the interference colors in the 4 quadrants are kind of white or cream color. They're not really that exciting in color because low birefringence means low order colors, and that's all things we talked about in that first part of the optical mineralogy videos, so go check that out if you don't know what the low order means or low birefringence means. But an example of a high birefringence mineral such as muscovite can have much cooler colors that actually can increase interference so much to produce what's called isochromatic rings that are concentric along the optic axis. And so this is something we can see in this example. But what about if the grain was oriented so that the optic axis was parallel to the microscopic stage rather than perpendicular to it, as we can see in the cross example where we get this perfect interference figure? Well, if it's parallel to the stage, the light would be allowed to vibrate in both the E and O directions, so the extraordinary ray and ordinary ray directions, with maximum difference in RI. So that means that you've now got this oval section going through that optical axis. If you can imagine that, it's not actually labeled on this figure. We still have the circular section labeled, but if you can imagine an oval section going up and down, that would mean you have the maximum difference in RI values of your 2 perpendicular rays of light that pass through that thin section. That means that you'll have maximum birefringence, and when you rotate to its extinction position, then insert the Bertrand lens, you'll see an interference figure, same as the cross like before, but it splits apart and disappears quickly as you rotate the stage just a few degrees. And this is called a flash figure. And a centered flash figure is proof that the grain is at an orientation so that it's exhibiting its maximum birefringence. So now for determining the optic sign of your mineral, so whether it's positive or negative. We talked about this in an ideal case scenario when you actually are just looking at diagrams, but what about when you're looking through that microscope at your mineral? What do you look for to identify the optic sign of your mineral? So we'll talk about how to do this for uniaxial minerals here, and in a couple slides we'll talk about how to do it for biaxial minerals. So recall that we defined this optic sign value as negative if the extraordinary ray is the lower or minimum RI value, which is also going to be your fast vibrating ray, whereas it is positive if your extraordinary ray, or E, is the max RI value, or the slower vibrating ray. So how can we tell which ray is the fast or slow vibrating ray under thin section? Well, this is another thing we talked about in the part 1 video, guys. Just go watch it. I promise we talk about all of this. It's just a lot of things that I can't talk about unless you watch that part. So please go watch that. We talked about how light going through this thin section is vibrating in 2 perpendicular directions, and one ray is fast and one ray is slow. And we talked about how to differentiate between the fast and the slow ray by using what's called an accessory plate. So if we insert this accessory plate into the microscope while observing the interference figure, the interference colors change. We can see this because the before picture of the field of view shows a regular old quartz example where you have your cross, and then you have these gray quadrants of your interference gray color for your quartz. Whereas if you insert the accessory plate, specifically a first order red accessory plate, basically you can pick the color of your accessory plate and then you can see how much your interference colors either increase or decrease in order to understand if the fast and slow light ray going through your mineral lines up with the fast and slow ray of that of the accessory plate, which is known value. So we actually have the slow direction indicated on this accessory plate. That is indicated on all your accessory plates. So this rule is for slow direction going this way and your fast direction going along parallel with your accessory plate. So remember that your slow and fast direction of your accessory plate matter greatly for actually determining your optic sign, because in this case where you have your slow and fast direction indicated as such, your quartz mineral will have a positive optic sign if your first quadrant decreases in interference color to first order yellow, your second quadrant increases, your third decreases, and your fourth increases, and that would be a positive sign. And if it is the opposite of that, that's a negative optic sign for this quartz example. However, if you had an accessory plate where the fast and slow directions were switched, these quadrants would also be switched. So remember, your accessory plate and the directions defined on your accessory plate matter. So look at that before you insert your accessory plate so that you can actually identify the optic sign. Now, don't worry too much if that was a little confusing. We'll literally repeat that for biaxial minerals, and it's basically very similar. So stick around if you want me to go over that one more time. So getting into biaxial minerals, we need to talk first about biaxial interference colors because they differ slightly from uniaxial ones, and then we'll talk about biaxial optic signs. So if you look at a biaxial mineral grain and rotate it to extinction, then insert the Bertrand lens, the interference color will look similar to the uniaxial cross like shown here on the left. However, upon rotating it 45 degrees, the isogyres split to maximum separation. What the heck does that whole sentence mean? Well, your isogyres, if you remember, are the black lines that make up your cross in your interference color. Now, if you rotate it 45 degrees on your microscopic stage, you will see the isogyres split apart from that cross. If they do not split, so if you have your stage rotated 45 degrees and they look like this leftmost figure on that figure at the bottom of the screen, then that means you're looking at a not biaxial mineral. It's probably uniaxial, because what that means is that your 2V angle or your optic angle, which only applies to minerals with two optic axes, so biaxial minerals, is 0. And if it's 0, it's uniaxial. If there's no angle between your two optic axes, there's just one optic axis and it's uniaxial. So by looking at how much your isogyres split, you can tell the optic angle, your 2V angle of your biaxial mineral. And like I said, if that angle is 0, it's uniaxial. If we see a split, but both isogyres are still in the field of view, then your 2V angle is likely small, but it's still biaxial because they split a little bit. And so we can see this in this example down here. And then if they split even more, your 2V angle is a little bit larger. In their example, it's 30 degrees. Then we can see 45. You're definitely not going to see both isogyres in your field of view. And then we can see 75. You only have one isogyre in the field of view and it's getting straighter, less curved. And then 90 is literally a straight isogyre in your field of view, and that's because they're at their max separation and you really don't have an acute and an obtuse angle. You just have 90 degrees in between your two optic axes, and so they're at their max separation, which is why you get this straight isogyre across your field of view. So we can basically see a summary of your 2V angles and the isogyres they would produce in this figure here. If you have a 2V angle of 15, you get this big curve here, and you'd likely see part of your other isogyre in the field of view as well. Then if you have 30, it's curved still, but less curved, and your other isogyre is probably leaving the field of view. 45, still curved, less curved, and then all the way to 90, which is straight. And I guess I'm ahead of myself again here. If your 2V angle between the two optic axes is 0, then your mineral is uniaxial. It has to be above 0 to have two optic axes and be biaxial. And a general rule of thumb is that that if your 2V angle is less than about 55 degrees, your isogyros will remain in the field of view. If you start at the extinction position of the mineral grain, insert the Bertrand lens, and rotate it 45 degrees. However, if it's over 55 degrees, you're not going to be able to see both isogyros in the field of view at that orientation or rotation of your stage. So there are two important types of biaxial interference figures that we need to define here. Basically, you have your acute bisectrix figure, which is abbreviated BXA and shown here on the left. And then you have your obtuse bisectrix figure, or BXO, and that's shown here on the right of this figure. And why are there two main biaxial interference figures? Well, that's because you have an acute angle in between your two optic axes and an obtuse angle. And so if your mineral grain is oriented so that we're looking down at the acute angle in between the two optic axes, you're going to see your acute bisectrix figure. Whereas if we're looking down at the obtuse angle of your biaxial mineral, then you're going to see the obtuse bisectrix figure. And again, if your 2V angle is 90 degrees, these two figures are going to be the same because there's no obtuse and there's no acute angle. They're both the same angle, and that angle is 90 degrees. So you're just going to have the one interference figure for that type of mineral. So what about determining optic sign of biaxial minerals? So determining the optic sign for biaxial minerals is pretty similar to determining that of uniaxial minerals, as we talked about previously. Basically, we insert the first order red accessory plate, and if the interference colors in between your two isogyros increases, so for example, from first order red to second order blue, then it's biaxial positive mineral, so your optic sign is positive. And if it were to decrease to first order yellow, it is a biaxial negative mineral. Now, if you cannot see both isogyros in the field of view when you're looking at a biaxial mineral, which is common, again, if your 2B angle is over 55, then you can observe which way the single isogyro seems to be curving. And if the color increases on the convex side of that isogyre, then the optical sign is positive because that's the in-between part of your two isogyres. If you were to find the other isogyre, it would be that direction. Now, again, remember that the slow direction is defined here as going perpendicular to your accessory plate, and the fast direction is parallel to the accessory plate. So remember that if that were the opposite case, which there are accessory plates with the fast direction perpendicular and the slow direction parallel, then the color increase and decrease would be opposite than what we've talked about. Therefore, if that was the case, the first order yellow decrease in between your two isogyres would actually indicate a biaxial positive mineral rather than the opposite, which is what we talked about here. So remember, the definition of your slow and fast directions on your accessory plate matter greatly for using this technique for determining optic sign. So now we've discussed all of these features that are shown on this mineral identification chart, which is like the ultimate chart for identifying minerals. Now, in reality, are you going to need every single one of these features to identify a mineral under thin section or even in hand sample? No, you're not, because there's a lot of ways that you kind of get used to knowing what mineral you're looking at and understanding its behavior before needing every single one of these features to figure it out. However, there are some minerals that are really hard to distinguish, and if you want to get real specific with it, you're welcome to go and explore every single one of these features. But likely, if you don't have anybody asking you to figure out the 2V angle of a mineral, you probably never will have to. But if for some reason you did need to know this, then I'm glad you watched this video because we discussed all that and now you know. And I also understand that it's really hard to understand some of these concepts without actually looking at examples of minerals under thin section rather than just these diagrams. Even the ones that are pictures of what the mineral should look like under thin section, I feel like they're still really kind of separated from what you'll actually see under thin section. So I'm hoping that in the future I can make some videos where I actually put the camera down the microscope, or well, yeah, down, you know what I mean, not down the microscope, but like show what I'm looking at in the microscope so you guys can understand what's actually going on, what you'll actually see, and kind of do some practice videos like that, not just for the features we talked about in this video, but also the previous video and other videos I've done where we talked about what to look for in thin section, because I think that will be really helpful for just knowing what to actually look for. And, you know, hopefully that'll be soon. If you want to go check out my channel and see if those kinds of videos are up, you can do so. But that kind of just depends on how quickly I get access to a petrographic microscope, I guess. So anyway, the upcoming videos on this mineralogy playlist are the metamorphic minerals song and the sedimentary minerals song. Like I mentioned, I have a crystal systems song. I also have an igneous minerals song, and I'm going to come out with these two songs as well because I think they do go a long way in terms of helping people remember the minerals and crystal systems or whatever it may be in the song. And so hopefully these can help you remember these minerals if you need to remember these minerals for an exam or anything. And in terms of lecture content that I have coming up, we finally have the new playlist coming out, Igneous Petrology. I hope you guys are excited. I'm really excited for this one. I wasn't really going to talk much about Igneous Petrology on my channel, but you guys really requested it a lot, and so I started looking through my old textbooks, and I've made a few lectures already, and I'm really excited for you guys to see what I have coming out on that playlist. So I hope you go check it out. And lastly, the major reference I'm using to make this video is Earth Materials Introduction to Mineralogy and Petrology by Cornelius Klein and Anthony Philpotts. And if you want to go check out this book, it is linked in my description. So that is it for this video. I hope you enjoyed, and thanks for watching. I'll see you guys next time. Bye. This is hard to explain. I'm not making any sense. Okay, let me try again. I said that really weird. I don't think I had that many bloopers for that video. I'm literally so sad. This feels so weird.